Orthogonal is a lot more general.
Okay.
So perpendicular is only if you're talking about in 2 dimensions.
Okay, orthogonal.
But in the 3 dimensions are more, you call it orthogonal, not perpendicular.
Okay.
They mean the same thing. It's a dimensional issue.
Okay.
Yeah, but from now on I'm going to start using the word orthogonal instead of perpendicular. It's more general. Anyway, questions on 10.6?
Yeah. Question number 9, part C.
And you're doing the second edition, right?
Second edition.
9C,
Yeah.
which asks us to do what?
It says find and identify the trace. What if we change the equation from x squared plus y squared plus 2y minus z squared equals 0?
Wait, this is x squared plus
Y squared
minus
plus 2y minus z squared equals 0.
Was that the actual equation?
The original equation was x squared plus y squared minus z squared equals 1.
Oh yeah, they had a 1 here instead?
Yeah, and no 2y.
Oh, yeah.
And I
Okay.
didn't,
Well, why did you, so where did this come from?
this is, what if we change the equation in part A to this? Now, if the original equation is x squared,
So this,
so the original equation is a hyperboloid in one sheet.
first of all, this equation I would look at as this. Right?
Okay,
You complete the square to put it in standard form and then you do that.
right, oh,
Right, so.
okay, so it shifts at 1 unit.
Yeah,
On the
so
y direction.
Y is going to shift to y
Down
minus
1
It's
to
gonna-
minus 1. Okay, okay, that's, I didn't know how to look at that, thanks.
Okay. Other questions?
Number 21.
You're in the second edition? What did that say?
Which one, 31?
Yeah.
Find an equation for the surface consisting of all points that are equidistant from the point -1, 0, 1, and the plane x equals 1. Identify the surface.
Oh, sorry.
And the plane z equals 1?
No, x equals 1.
Negative 1, 0, 0.
No, but that's in the first edition.
No, second edition is -1, 0, 0.
0, 0.
So they're the same question?
Yeah,
Yeah, it's sort of this.
so there's a
Does
plane.
anyone kind of see what kind of surface this should be?
Think of it in 2 dimensions and you think of a parabola.
In 2 dimensions would be a parabola, right? A parabola is a point that is equidistant from, a parabola in 2D is a curve that is equidistant from a line and a point, right? Plot all points that are equidistant from the point on a line, you get a parabola, right? In 3 dimensions, of course, it's going to be pretty similar. It's actually going to be a paraboloid, right? So you should be able to derive the equation of a paraboloid from this, right? But when it's talking about the distance formula, right? It's talking about distances, so you're going to think distance formula. So what do we know about the distance from a point? Right, so you say let the set of points be x, y, z. Then we want what to be true? We want the square root of x plus 1 squared plus y squared plus z squared, right? That's the distance of those points from that. We want that to be equal to the distance to the plane x equals 1. Now, how do we find that?
The formula for.
There's a formula, right? A distance from a point to a plane. So we had that the distance from, so now we're going to recall, distance from, I think it's x1, y1, z1 to ax plus by plus cz plus d equals 0 is, what's the formula?
Absolute value of the plane function ax plus by plus c.
Isn't it ax1?
Yeah.
Yes.
Ax1 by
Plus d?
Plus D.
over
The square root of a squared plus b squared plus c squared. Right? So now we're just going to equate that to this formula. Now in our formula, the plane is just a is 1 and b is 0, c is 0, and d is negative 1. Right? So this should just be the absolute value of a is 1 times x1, so just minus 1. D is minus 1. So that's just going to be 2, right? Divided by the square root of 1. Right? So basically you're just solving x plus 1 squared plus y squared plus z squared is equal to 2. Right? Which is x plus 1 squared plus y squared plus z squared equals 4. Was that looks like a sphere. Is that the right formula?
Well, I got an elliptic paraboloid.
Did I write down this right? Is this it?
That's the right formula. I think maybe you plugged the wrong things into it.
Let's see, my A is actually 1.
Is it? When x equals.
How do you know D is negative 1?
Right, yeah, okay. So your normal vector could be 1, 0, 0, right?
Yeah. So A is 1, this is 0, this is 0. Right?
Where did
So
you
that's
get
all.
the 1 from? Which is it?
Here, the plane.
The plane is
I have
A.
1x plus 0y plus 0z minus 1 equals 0.
Okay.
So A is 1, B is 0, C is 0, D is minus 1.
How do you know D is minus 1?
X equals 1.
Because x equals 1, I bring the 1 over,
Oh.
get minus 1. Okay? And so and then here, this would be the x1, y1, z1, right? So then I'd have minus 1 times 1, which just gives me this. And then this would be 0 and 0. And then I would have the d, which is minus 1. That should be fine. Into a plane
Where's the expression in the radical come from? That, the very first one, on the bottom. Down
Come again?
x plus 1 squared plus y squared plus
Should be X.
X plus 1 squared plus x.
Yeah,
Oh,
what-
distance formula, right? So I'm saying the set of points is this, and I want the distance from that to this.
Oh, okay.
So that's going to be the distance formula here.
Oh,
I'm thinking that equation we're applying it wrong.
no, yeah, I think. Okay, you shouldn't have plugged in the x coordinate at the point. You should have just plugged in x generally.
Right, that's what I'm thinking.
That's what I did.
Right, we don't want the, we are, considering this to that, we are already done. We actually want the general point. So this is actually going to be the x1, y1, these are actually x, y, z in this example. Right?
Right, yeah.
So then this would actually be minus x.
Yeah.
Yeah, we already measured the distance from the point.
No, it should just
Now
be,
we're looking
it
at
should just be x, x
Oh,
minus
it's X
1.
minus 1.
Yeah.
Okay, so that would make more sense. So this is x minus 1. Okay, now that's going to give you a paraboloid. Okay, so now you solve for it. You have x plus 1 squared plus y squared plus z squared equals x squared plus x squared minus 2x plus 1. And you write this one out. This is x squared plus 2x plus 1. So now the x squares die, the 1's die. And so this guy would look like this would be 4x equals minus y squared minus z squared. Or x is equal to right? Or you can think of it as the negative of this, that's also fine. But we know that this x equals y squared plus z squared is a paraboloid opening how?
Towards the door.
Towards the door.
Along the negative part of the x-axis, like Muriel.
Along the negative part of the x-axis. That's correct. And you can actually draw the traces if you're ever not sure, right? If you draw it like in the xy plane, right? If you're drawing x equals minus y squared, or minus a quarter y squared, it would look like this, right? So you're opening towards the negative. So this is, it's going to touch 0, it's opening that way. Right? And the plane x equals 1 would just be a plane like here. Right? And then the point we're talking about is going to be inside here somewhere. Yeah, on the axis here.
So it is like a 3D parabola.
Yeah. So that one came down to using the distance formula that we know between points and the distance formula that we know for a point to a plane. But here we left the plane in, we have to leave the points general because we're solving for x, y, and z. That could be any arbitrary.
Are the test questions going to be this hard?
Hmm?
Are the test questions going to be this hard?
The test questions are going to look like the review problems that I posted on my website. Very similar. Other questions?
29?
29.
Second edition?
Yeah. You want me to read it?
What does it say?
So sketch the region bounded by the surfaces z equal square root of x squared plus y squared and x squared plus y squared equals 1 for z is between 1 and 2.
Okay, what's this guy?
The top one?
The top one, yeah.
It's a cone.
It's a cone, just the top part of a cone.
Oh, right, just the top part.
Just the top part, because it's not z squared equals, it's just a positive square root.
Ah.
So we know it's not going to give us a negative part. So that part is just going to go like this. Right?
Doesn't z have to equal 1 though? Because then it would
Not yet. We plot one at a time and then we sort of see how they interact.
So they're two different. They don't do anything with each other. They're two different graphs.
Yeah, two separate graphs that we're going to sort of clash together. Right?
Right.
So now what does this guy look like? Circular cylinder, also going along the z, right? Right, so this is just like a cylinder that's cutting through that cone, right? Now you're going to want to cut it between z equals 1 and 2, right? And you're going to see what that looks like. So, where would this cylinder meet the cone in the first place? Where would they actually touch each other?
Well, we'd have to find the points of intersect.
How do you do that? 1, 1. When z equals 1, right?
Yeah.
So these guys intersect. Right, x squared plus y squared is 1, you just plug it in here. Z equals the radical of 1, right? So this will actually touch. When it touches here, it will actually cut it at z equals 1. And then you want to go even further up to z equals 2. Right? So that's going to be another one. And we want it bounded by all of them. Which part are we talking about now? So that's sort of the general shape, but it has to be
Bounded by the
bounded by all
surfaces.
of them.
That's from 1 to 2.
But it's
So
just
Z
a
from 1 to 2
cone.
is the top and the bottom, but how is it bounded between the cone and the cylinder?
But the cylinder is only
It's just
radius
the-
of 1.
Right, so this is going to be out here. Right, so it's hollow.
Okay.
It's like a washer that actually increases in thickness as they're going up. Now, as I was saying to Nettie earlier, this is actually an important kind of problem because this is the kind of problems that you're going to be using. They're going to be describing regions to you that's bounded by several other surfaces, right? So you need to know how to draw these surfaces one at a time and then sort of connect them together. It's just like in calc 2, right? When you're asking, find the area of the region bounded by blah and blah, right? You have to draw each curve separately and then figure out what region they're talking about, right? This is the same thing. And in 392, they do that all the time as well. So here's another example. Sketch the region. What would that region look like? Up here. know what this looks like?
No, I have a question. What's the constant to the right of this one?
4. Over here?
Yeah.
Yeah. X squared plus y squared plus z squared equals 4.
I can't. How do you, I'm above the cone, I mean, doesn't the cone keep going upwards forever?
Yeah, so that's sort of a terminology. What they mean by that is this, right? The cone is the actual surface, right? So if you're above the cone, it means you're in here.
Okay, I mean, that's.
Right? Like I'm above the floor. I'm standing on it.
You're right, oh.
Right? So if someone is standing on the cone, they're above the cone.
Okay, right, because it's not a volume space, it's a.
No, it's actually empty in here.
Right.
So above the cone means standing on top of the
I
surface
see.
inside. Yeah.
Gotcha, okay.
See the little stick there? So what does this look like?
A math problem.
It's an ice cream cone. Exactly. So there's the cone, which is just that guy going up like that.
And then there's a
sphere.
circle.
Right? And we want to be above the cone, which means we're standing on the cone, but below the sphere, which means when we look up to the roof, we see the sphere. It's describing the region in the middle here. So it looks like an ice cream cone. Here's another question. If I was shining a light directly vertically downwards, what would the shadow look like? It would be a circle, right? What's its equation?
The radius,
Is equal to 2.
no, why would it equal 2? The radius at the top of the cone isn't 2.
4 equals 4.
Because the cone and the sphere intersect at different points.
They intersect. I have to intersect this with that, right?
Right.
From here, z squared is equal to x squared plus y squared, so I plug that in here. I get 2x squared plus y squared. Right? By substituting this z into that. Right? And so you just get x squared plus y squared equals 2.
That means the radius is weird.
So this is a circle of radius radical 2. That's going to be important later. Remember when I said polar
And
coordinates is coming back with a
obviously it
vengeance?
has to be
It's going to come
small.
back with things like that. Because you're going to be doing polar coordinates in the xy axis while doing something else in the z axis. So, just a preview. Okay, how do we do this one?
Well, one is a sphere
What is this?
and one's a cylinder.
X, 1, z, so let's see.
Radius.
Sphere.
And a cylinder.
You know, its radius is going to be like, its radius is 2. But the vertical cylinder has radius 1. Right? So,
Right.
I know that cuts through. Okay, so what does it look like? Pipe with rounded edge. Rounded top and bottom. I If I look where the cross section in the xy plane, what equation is that? It's going to be the same one. X squared plus y squared equals 1. Here's a question going back to polar coordinates. What if I asked you for... I'm wasting time, I should be finishing in 10 seconds. I'm just coming up with these other. Okay, but it's outside.
Outside the six.
But inside.
Space.
Well, then it would be those two sections on the
The
outside.
two sections that we didn't put this time, okay? So this is x, this is y, this is z. We have that sphere happening, we have this guy happening.
So it
But
would be
now I
the
only
two
want
half
the
moons.
outside. So this is hollow now. So it's like you take a tennis ball or something, you drill through it, right?
Wouldn't it be just the two slices on the outside? Like you'd have
No,
two
it
half
would wrap all the
moons?
way around.
Oh, I see.
Because remember,
what
the
you're
sphere is
saying.
radius
Right,
2, and this
And
is
this
radius
radius
1.
one.
So it's completely enveloped in the sphere.
Right.
Okay? So now here's my question. If that solid intersects the xy plane, what is the region it intersects?
Same
Just-
thing.
No, then it has four intersect points on the xy plane.
Not just 4 points. What would the intersection look like? If I'm drawing the xy plane, what does the intersection look like?
If you look at it like from the top, it would look like a ring.
Like a washer.
Looks like a washer. Right? Where this is 1, that's 2. Right? Because that's 1, there's going to be another circle here for the sphere. And then this is hollow, so it's just the outside here. Describe that region to me.
Yeah, what is that?
So this is the region we're looking at.
It's the area between x squared plus y squared equals 1 and x squared plus y squared equals 3.
Tell me in terms of equations.
In R3 or R2?
In R2, it's fine.
Okay, so x squared plus y squared plus z squared equals 1. No, equals 4 minus x squared plus y squared
It's z
plus z.
squared.
It's
z
not
squared.
minus, no.
Well, you have to subtract the inside from it, don't you?
It's an
What you
integral.
said.
Just the integral.
I meant, yes, I meant the integral.
It's 4 times.
I never actually defined the area. That's very different. I actually described the region.
Circle x squared plus y squared equals 4.
Well, you can write it as x squared plus y squared. It has to be
More than
bigger than 1
One.
or less than 4. Describe the region in polar coordinates.
Oh, less
Cosine.
than equals 1 and equals 2.
So this is in what we call rectangular coordinates. I want the description in polar coordinates. Yeah.
1 is less than theta is less than 2.
R
Between 1 and 2.
between 1 and
2.
theta.
0 and 2.
All right, because 0 and 2.
All right, this is a full revolution. Okay. Let's move on to 10.7. That's sort of how you're going to have to dissect shapes later on, right? So they're going to just tell you two surfaces that they're clashing together. And if you're going to do an integral especially, you're going to have to be able to figure out, okay, what's the projection in this plane? What does it look like? How do I describe it? Because these are going to be the guys that tell you how to set up the limits on your integral, right? But then you sort of have to draw a picture to figure out how to set that up in the first place, right? So you're going to draw these guys, figure out what it is, then you draw the projection in a certain plane, then you figure out the description, and then you know, oh, those are the limits on my integral that I can do it, right? But that's later. That's chapter 12. Okay. And that's why we need polar coordinates and things like that. Okay, so let's continue from that tangent. No pun intended. We're going to learn about tangent vectors, so that's good. Okay. Set of define what a space curve is. Let's clarify, we know it's a curve because there's only one parameter. It means it has one dimension, so we can call it a curve, not a surface. Right? There's only one parameter, t, right? And so you actually drew space curves today in MATLAB. Right? So that's basically the idea. So there's this curve in space. One way you can describe it is in terms of a vector function, which you can call a space curve. And basically all the points here are given by the position vector r of t for some particular t value. Right? So that's how you trace them out. You can literally plot points by plotting it along the tip of this vector. Right? So basically that's how, even when you do it in MATLAB, that's sort of how it does it. It plugs in a bunch of coordinates, and for each coordinate, it gets a vector that it looks at as a position vector, and it plots a point at the terminal end, right? And it does this over and over and over until it connects a line. So now I'm going to give you some examples of space curves. better left to another MATLAB exercise because the line is going to be hard for you to see in 2 dimensions. B is not going to be so bad. Okay, let's start with this. What kind of curve is this? Huh? It's a line. How do you know it's a line? All components are linear. X is like x naught plus at, y naught plus bt, z naught plus ct. Has the form of a line. Each component is a linear function. Therefore, we know it's a line. So how do we know how to plot it? So in A, RT is a line through, give me a point it passes through. Parallel to right. That's my description, and now I can sketch it. It's not going to. You're not going to probably. It's going to be hard to visualize a line. But so I know the vector 2, 3, 4. It's sort of pointing out this way towards. It's in the first octave. And 1, 2, 3. So 1, 2, 3. Sort of combine these guys. So if this was the planes, that's your x-axis, this is the y-axis, this is the z-axis, the line is actually shooting out into the room like this. I mean, you can't really see that from the picture, but that's what's happening. B. What kind of curve is that?
Cylinder.
Huh?
You know, again there.
No, that's a spiral.
It's a spiral, right? It wraps around the cylinder. Yeah. It's called a helix. Okay, so tell me how are you going to figure out how to draw it?
Sine function and the cosine function.
So what does that mean?
So plot the values against like the plot from 0 to 2 pi.
Yeah, so this is x and this is y, right? So what would that look like? If x is 2 cosine t, y is 2 sine t. Yeah, x equals 2 cosine t, y equals 2 sine t. That looks like r cosine theta and r sine theta. We know that x squared plus y squared is r squared. So we know that everything is happening on the cylinder of radius 2.
So when t equals 0, x is going to be 2, and y is going to be 0, and then you just, as you go in a
Right, so it would be
clockwise
on the x-axis.
Right.
Right, and then as t increases, it's just going to spiral going around this circle.
Like a spiral staircase.
It's going to be traveling counterclockwise if you look from above, right? So if you're looking down, it's counterclockwise.
How would you make it go clockwise? Would you
The x
just,
is the cosine.
I'm sorry?
X is cosine, right? Remember, that's how sine and cosine were developed from the unit circle.
Right.
Remember, the x
So-
coordinate is cosine, the y coordinate is sine,
So if I
and the
wanted it
functions
to
were
go,
developed in such a way that it goes.
if I wanted to go clockwise, then would I put negative cosine?
You switch.
Yeah, or you could switch. You could make it x sine and y cosine.
Oh, okay.
And don't really want to mention that now. In 392, there's going to be a different way to switch where you negate something. Right, but it could also, and it continues actually going down. Right, it will continue in both directions unless I give you some limit for the z. Right. Oh, we still have more examples. Find a vector function that gives a line segment from that to that. Remember what the formula said?
So it's 1 for t on 0 to 1. It's 1 minus t.
1. Yep.
Oh.
The direction vector is given by the coefficients of t.
Yeah, but how did you find out it was parallel?
Because that's what the direction vector is. The line, the vector is parallel. I'm not sure what you mean. Right, it comes from the formula for the equation of a line. Right, where it was x0 plus at, y0 plus bt, z0 plus ct. Right, where your v is actually the abc, which is a vector that's parallel to the line. Right, that just ends up being the coefficients of t. So I know that these guys are the vector and the constants are the points. Just from knowing the formula for the equation of a line, you can sort of pick it up. So yeah, what are the components here?
It's 1 minus t into 1.
1 minus t.
Nice statement.
Like,
Oh, you're doing from the book.
Yeah.
Okay, like give me the final answer. What would it look like?
1, 2, 3.
takes forever to compute in the form of the book, right? It's just remember what we did the shortcut,
Right, one
right? You start with 1,
Four.
you have to add 3 to get to 4. Start with 2, you have to subtract 7 to get to 5. Start with 3, you have to add 3 to get to 6. Right? Curves of intersection. Any ideas?
First one is a circular cylinder.
Mm-hmm.
Set one's a plane.
What axis is that going on?
The y. So,
I'll give you a hint. One of the easier ways to parameterize something like this is to first parameterize that and use its parameterization in that.
I'm actually not sure what I'm supposed to be seeing. I'm looking for a vector function over the curves that intersect between these
Oh,
two.
yes. So
So I'm not sure exactly what I'm looking for.
it's going to sort of look like an elliptical curve in space. Because there's going to be a plane. And then there's, well, it's going to be, sorry, I'm throwing it on the wrong axis. There is a cylinder that's running along the y, right?
Right.
And then there's a plane that is going to cut through.
Oh, okay.
Right? And the plane is that, right? Which you know it's going to intersect 1 here, 1 here, 1 here.
Right.
So there's a plane cutting through the first octant like that, and then there's a cylinder cutting through that. I want the outline of the cut, which is going to cut it in a slant direction, so it's sort of going to look elliptical. Right?
Okay.
I want to find a parametric equation for that. Yeah?
Since you have x squared plus z squared for the first equation, could you square the second equation so you would have an x squared plus a z squared?
Yeah, but then you get an xy and an xz and an xyz.
Oh, right, yeah, you would have too many terms.
How do you parameterize this by itself? Like, what if it was to parameterize a circle?
x equals 2 cosine t.
You could say x equals 2 cosine t, what, and z would of course be the sine.
How do you know which one is cosine, which one is sine?
It won't matter.
Or won't it?
Because one way you get the curve by going around this way, the other one you get the curve by going around this way, you end up with the same curve. Right? I never said, oh, I want to go around counterclockwise. I never specified a direction. So it really doesn't matter. But I'm just used to saying x is cosine from my polar coordinates days, so that's sort of the habit I fell into. And so now if I know that, how can I make sure it intersects with that? You just plug it in. This means that you'd be able to write z, you'd be able to write y as 1 minus x minus z, which is 2 sine. In other words, you'd be able to say r of t is equal to, the x is 2 cosine t, the y is 1 minus 2 cosine t minus 2 sine t, and the z is 2 sine t. And you can plot that in MATLAB if you'd like, and you'd see that you'd get the shape that you'd expect. In fact, you can plot the plane, and then the cylinder, and intersect it, and then compare that with a graph of this vector function. Because I know some of this is hard to visualize when you're seeing it for the first time. That's why I taught you how to do curves and surfaces in MATLAB today. But one trick with parameterizing curves of intersection is sort of, in general, what I'm doing here. You sort of parameterize some of the variables, and then you solve for the third one in terms of the other guys. How about E? Again, it's sort of the same idea. If you can solve for everyone in terms of one variable, then solve for the third guy in terms of the other
Right,
two.
I mean, here, it's given this basically, we don't have to do any fancy parameterization, you just plug in 1 plus y squared.
For X,
Right.
right. And then you can solve for Z. And
etc.
right, so here, plug in 1 plus y squared for X into X plus Z. So this would mean that your Z is equal to 4 minus y minus 1 minus y squared. So your Z would be 3 minus y squared. And you can actually parameterize it in terms of y. For some people, for some reason people like t, so you can say y equals t, which means that your x would be 1 plus t squared, and then your z would be 3 minus t squared, and so you get the vector function. There'll be plenty of those to practice on the homework. I hope there are. There aren't, just find another calculus book and practice those. Now let's look at R prime. This is F prime gives you the slope of F, which sort of tells you if it's increasing or decreasing, gives you a sort of general direction of where the curve is going. So in R prime, it's sort of the same way. R prime gives the direction. So that means if I have a general curve, do something, and at this point, if I draw a tangent line, right, so this is at the point r of t0, then this direction vector for the tangent line would be given by r prime at t0. Right? the derivative sort of gives you this direction of the tangent line, right? Just like before. Hence, our t is called, prime t is called tangent vector. And we define the unit tangent vector as, of course, the tangent vector divided by its magnitude. So, let's do some examples. One more definition, then we do the final examples. There's a lot of information packed into that I should probably talk about. So what happens at a point where the function is continuous but the derivative is undefined? What kind of points do that? A cusp, right? A sharp corner, an edge, right? So if your curve has a sharp corner, at that point, the derivative is not defined even though the function is continuous, right? It's a critical point anyway, right? So that would be jagged, it's not smooth because the derivative is not defined, but it's continuous, right? It's sort of the same idea actually happening here. Right? By when we say that r prime is 0, right? It's sort of equivalent to the derivative not being defined in some sense. Can anyone see why?
It's not moving in any direction.
Right. 0 is not. What direction is the 0 vector, right? It's parallel to everything and it's perpendicular to everything, right? Dot product with the 0 vector is always 0. Cross product with the 0 vector is always 0 vector. Right? So the 0 vector is like this guy that seems to point in every direction. Right? Like what the hell is the 0 vector? Where the hell is it pointing? No one knows. It's undefined, really. Right? You don't know the direction of the zero vector. It's perpendicular and parallel to whatever you want it to be. Right? So that's why if the derivative of a vector curve is 0, for all intents and purposes, it's undefined, and what that means, sharp corners happen there, and hence it is not smooth. Right? So the phrase "a smooth curve" is actually sort of intuitive, right? But the reason why is because of the whole sharp corner thing. Okay, just thought I'd say that. Okay, now let's just do some examples and get out of here. This will help you practice for the test, because there are some problems like this on the final example. It also says sketch the position, but I kind of forget. Can I get rid of this? Did you guys copy that down?
Yeah.
Can I get rid of it now? think it's also theorem 5 in the second edition. Okay, let's begin. Get out of here. How do you sketch R?
So I just recast it in terms of x, so x is 1 plus t, so t is x minus 1, and so I plug that into square root of t, and then I get just the square root of x, y equals square root of x, shifted 1 unit to the right.
All right, that's from parametric equations from calc 2 even. You learned how to get rid of the parameter and plot the function. By the way, if I wanted to plot like the tangent, the position vector to get to 2, I could plot it like this, and then the tangent vector would be like this. And so I think there are some homework problems that look like that, just in case. How do you find the unit tangent vector? By the form of, right? We know that big T is called the unit tangent vector. It's actually just the derivative over its magnitude. So this means we find the derivative of this guy, which is so this is going to be 4
squared. Sine squared. Cosine squared.
yeah, it's going to be 4 cosine squared plus 4 sine squared, which is just 4, plus that's the unit tangent vector. Right? Now we want the unit tangent vector at this point. So then t at pi over 4 is equal to where do we find that? Cosine of pi over 4?
2.
2 root 2 over 2.
Right. So it's just 2 minus radical 2 secant of secant squared. Secant of pi over 4 is
1 over root 3.
Secant is
1 over cosine.
is 1 over cosine, right? So secant of pi over 4 is just radical 2, and then we square it,
2.
right? And so secant, huh? And then secant here we know that that's radical 2, and then we raise it to the 4th. So we square it and then we square it again. So that's 4. So this is radical 8. Find the tangent line. What do we need to find the equation of a line?
A point and a vector.
You have the point, how do you find the vector?
You would create from R the
It's
normal.
a tangent line, which means the direction is given by
The derivative.
the derivative. Right, so our v is going to be given by r prime, which is going to be 2t, 2t, 1. All right, so at minus 1, 1, 1, which means t is equal to what? To get to that point, what do I have to make t equal to?
2, 2, 1. No.
220.
T is a single value. T is a parameter.
Oh, I thought we were talking about.
Right. I don't only need to find. This is the general direction for arbitrary T value, right?
Right.
I want the direction at this point, which means I need to know what T do I plug in to get to that point.
Negative.
0.
0.
Right? Plug in 0 here, I get negative 1, 1, 1.
Ah.
Right? So then V here, I'm going to plug in 0 in the derivative, is actually 0, 0, 1. This means the tangent line is x, y, z equals the point minus 1, 1, 1 plus t times the direction 0, 0, 1. For smoothness, what do we look for?
Tenuous except
Would the
constant.
derivative not be undefined?
So look at the derivative. We know it's 2t, 3t squared. All right. This means that your r prime of t equals the 0 vector if t equals 0. Right? So not smooth on any interval containing 0 as an eternal point. Right? 0's at the end points is fine. You can't. Any interval like from -1 to 1, we couldn't take that. It wouldn't be smooth there because there's going to be a sharp corner at the 0. This guy here, R prime would be that guy.
So it's going to be smooth everywhere.
Smooth everywhere, right?
Where you can get e to the t to 0.
Because R prime is not 0 for any t. Okay. We sort of went through that a little bit fast, so it might be confusing, but I'm sure if you read over that, it'll be fine. Because we're using very similar concepts to calculus 2 and here. So, yeah, that's it. Enjoy the homework.